we're on live, okay? Everything we say now is going to be put onto YouTube. Okay, so we're good to go. And I'll ask questions in a bit. Let me go to this first. Ponso, let me see if we can add her. I don't know if she's available. All right, thanks, Mingy. Talk to yourselves for 2 seconds, eh? Add people. There, she doesn't. I'm gonna. Oh. What one did you give me, dear? Yeah, let's go back. Okay. Yeah, you've given me the Marapula address. I don't think she's using that one. Okay, sorry about that. Mingy, I don't think she's using that one. All right. Anyway, so it's life, isn't it? Right, anyway, back to work. Oh, I've got a message. And the message is you switch off the microphone by clicking on the microphone icon, okay? And there'll be a line going through it, okay? That's the one she sent to me. Maybe, but it's not picking her up actually, dear. I don't know why it's not working. Anyway, let's get the video going because all of this is being recorded. Now, if you remember yesterday, we put hydrogen in a magnetic field, didn't we? We had something like this, and then my hydrogens were in here. Okay, and the take-home message was this. We had a graph, didn't we? Oh, that's awful. Let's get rid of that. Oh, okay, we had a graph, and this is energy. And this was degenerate state, and this is the flip state. Okay, so we had our protons were either aligned or opposed. Okay, and down here were the aligned protons. Here were the opposed protons. Okay, so if you remember from yesterday, these ones were opposed and these ones were aligned. Okay, and the energy gap there was HF. And then we said if we increased the external magnetic field, we'd have a bigger energy gap. I'm going to give it different proton colors there. Red protons now. Okay, so there you go. So this goes further up, doesn't it? The energy gap increases. And so what we have is delta E equals HF. And now this is F1, F2. So F2, the frequency for this gap, is going to be greater than the frequency for this gap, okay? Because this one is a bigger energy gap. H, don't forget, is Planck's constant. Okay, all right. Now, just to finish it off, this one was what we call degenerate. Degenerate. This one is in, and let me write this a bit more formally. This is when we have an applied external magnetic field. Okay, and this one is also, let's see if I can do something clever. Oh, look at that. And I'm going to copy it. And I want to paste it. Oh, well, I've never done that before. Oh, well, it's not working there, is it? Okay, look at that. I've messed it up. Anyway, it's all going wrong. Okay, let me get rid of this. Oh, it's what happens when you have a mouse and a pen. They neither work at the same time. Okay, so this is also an applied field, external magnetic field. Okay, but this magnetic field is greater than this field, and we see a bigger energy gap. Okay, so do we all understand what we talked about yesterday, and can I move on? Now I'm going to go to the questions here. All right, Ronald, how do I switch off? That's the one that she sent to me. Hover over Mr. Numbers video and click the microphone button. Yes, that's how you do it. Thanks, I did it. Okay, we're all good. Are we all good? Can I continue? All right, with today. That was pretty well a summary of yesterday's. She found her password. What do you mean by that? That means I can use that address? Yes, okay, let me try it then. Let me see. All right, guys, you'll have to amuse yourselves for 5 minutes, eh? While I try this. Oh dear, that didn't work. Where's the address? It still doesn't say it has it. It's weird. Let me see if I can find it somewhere else. All right, guys. I'm sorry about this. Just be a bit patient. I don't know if you can see what I can see here. Alrighty, let's go to my contacts. Okay. Let's see if I can find it here. Yeah, it looks like the same address. Okay. Wow, it's weird. I can't find her. But it's the same address. I don't know what's going on. For some reason or other, I can't get her. Sorry, we'll have to sort her out for next time. Okay, she's on. Oh, she's on. Oh, God. Oh, maybe she's on it already. Everything's good. Well, why isn't she answering then? Well, that's crazy. Anyway, let's get back to work. Oh, now we're all good, are we? Nicholas, she's on. She's on this. Okay. Well, thanks, Ponzo. Don't worry about us, dear. All right. So let's get back to work. Yes, are we all good? All right. So this is what we did yesterday, wasn't it? What we're looking at here. All right. Now I'm going to get rid of this, and there you go. All right. And now I'm going to do the machine. This is the Nmr Machine. Nmr Machine. Okay. And this is a schematic. Okay, which means a very basic diagram of the machine, the Nmr Machine. Okay, but it's all we need to know. Okay, so you have something that provides, this box provides the frequency. In other words, it generates a frequency. And the frequency, believe it or not, is in the radio waves, the radio wave part of the spectrum. So this box is going to be our radio frequency generator. Okay, and now this is our external magnetic field. Don't forget, it's a schematic, so it's very basic. And this is going to be a north, and this is going to be a south. So this is going to provide our external magnetic field. So this is our external magnetic field. All right, and right in the middle of this is our sample. Okay, and the sample is in liquid form. Okay, here. There is the sample. All right, and it's an organic thing. This is an organic compound. And what do we want to know? Well, we want to know the structure. What is the structure of this guy? I don't know. And this is what we're doing. Okay, now this sample, and this is a technical detail, so you don't have to know this, but I like technical details. It's spun very rapidly. Okay, it's spun on air. It's spinning. This thing is spinning around. Okay, so it's just a test tube. It's not even a full-size test tube. It's a much smaller test tube. It's spinning around in an external magnetic field, and the reason it's spinning around is so all parts of the liquid experience the same external magnetic field. It's a technical thing. So there's my magnetic field going through the sample. Okay, now watch this. This is my radio frequency generator, and that goes. It wraps around this, okay, and then it goes up to some sort of recorder, a recording device. So this is my recorder, okay, and this records absorbance. what has been absorbed. So the radio frequencies go in, okay, they go into the sample, and then something records what has been absorbed. Yeah. So if nothing is absorbed, okay, I'm going to draw a graph of absorbance. This is absorbance. Okay, and this is frequency. This is my radio frequency. If nothing is absorbed, I'll get a line, just a dead line on the bottom. So if nothing's in this, nothing is absorbed. And this is nothing absorbed. Okay, now, so that's basically the setup. I put my sample in here. The sample goes in a very strong magnetic field here. I shoot radio frequencies at it and see what it records. Now, the radio frequency thing here, it doesn't just produce one. This produces a spectrum of radio frequencies. Okay, it doesn't produce one. It goes through a whole band. All right, and there's countless billions of radio frequencies, and it scans them all. Okay, so this scans the radio frequencies. They go in here. The sample absorbs, and the recorder records what is absorbed. Okay, and this is our external magnetic field. Now, you probably won't understand this diagram until we do a little bit more. But are we okay with that kind of? Any burning questions now? No one? No burning questions. Okay. No one? Everyone's good? Okay, cool. All right, let's go back. Oh, who's that? Oh, Ronald, turn the video off. Bloody hell. And the... Oh, God, Ronald, what's wrong with you? Turn the video off. All right, click on the video, but well done. Now turn the microphone off. Ronald, that's scary. I don't want to see anyone's heads. Just it freaks me out. Ronald, your microphone's still on. Ronald. And this is getting uploaded, don't forget, Ronald. No one's going to see anything, though, don't worry. Ronald, bloody hell. Right, anyway, so are we all good? A quick thumbs up, can I move on? Thumbs up, thumbs down, whatever you want to do. Good, Terry says good. All right, now this diagram here, oh, let me see, was that a question? Nicholas says why. All right. Now this is the setup. Now this won't mean an awful lot to you at all until we've done the next bit. Okay. And so we're actually going to do a sample now, and it all will come together. I promise you. And hopefully it will come together today, but we shall see. Okay. So now let's have a sample. My sample. And I'm going to take a very simple sample to start with. I'm going to pick this sample. Ethanol. Okay, nice and big. There's a sample of ethanol. And this is going to go in my machine. And this is going to be what I'm going to see by my recorder. Okay, now, this way, here, this direction, the frequency increases. So how do you spell frequency? Frequency increases. Now, if I could be with you, I'd explain why the frequency increases this way, and it's quite interesting because in the old days, these recorders used to just be a pen going up and down, okay, and the paper used to move, and the pen just went up and down. So this is a throwback to the old days when the paper moved and the pen stayed in the same place. Yeah, so the paper moved from right to left, and as the paper moved, yeah, the recordings came. Okay, I'll have to be with you and show you the paper moving in front of you, because it's not complicated at all, but it's just one of those things. It's very visual. Okay, so the frequency goes that way, and on this side we have the absorbance. How much is absorbed? Okay, now we'll talk about these numbers later, but let's have a look at this. Right, now if I do ethanol, and this is ethanol, ethanol. How many different types of hydrogen are there? Well, what does it mean to be a different hydrogen? It means, or the same hydrogen. When I say how many hydrogens, when I say this, how many types of hydrogen are there? Okay, what we mean by that is how many chemical environments are there? Okay, and let's have a look at this hydrogen here. Now, I'm going to call this hydrogen A. Now, this hydrogen is exactly the same as this hydrogen. Okay, why is it the same? Because this hydrogen is connected to a CH2, and so this hydrogen, the one I'm looking at, is connected to CH2, and the CH2 is connected to a CH2, and this CH2 is connected to an OH. So this hydrogen here is exactly the same as this hydrogen, and it's exactly the same as this hydrogen. So all of these three hydrogens are said to be in the same chemical environment. Now, let's have a look at these two hydrogens. Now, this hydrogen is not the same as this hydrogen because this hydrogen is connected to a carbon, which is directly connected to an oxygen. But this hydrogen, this one here, is connected to a carbon that is connected to another carbon. So these two are not the same as these three. This one and this one are not the same as these three. Okay, and obviously, as you can see, this carbon here is totally different. Sorry, this hydrogen here is totally different. So in this particular molecule, there are three chemical environments for our hydrogen atoms. Okay, and don't forget, we're looking at hydrogens because in each hydrogen atom is the proton, and that's the one we're trying to look at. Remember? So there's three chemical environments. So this guy will give, so ethanol will give 3 peaks. Okay, and now let me draw them. Okay, this is going to be pretty ugly, I'm sure. Okay, so there's a peak there. There's a peak there. Ah, that was awful. I knew that would happen. So let's go along. There's a peak. There's a bigger peak. And there's a bigger peak. Okay, now let's have a look at this. This is increasing frequency here. This peak here is produced by the HA hydrogens. This peak is produced by the HB, and this peak is produced by the HC. Now, if we were to, and I'm not going to do this, but if we were to work out the area of this one to the area of this one to the area of this one, the ratios of these would be 3 is to 2 is to 1. And why is that? Well, very simply because there are 3 types of hydrogen A. Okay, so they're going to absorb at a ratio of 3. There's 2 types of hydrogen B, so they're going to absorb at a different ratio. And there's 1 type of hydrogen C. So the areas under the peaks, what we call the integration peaks, if we integrate the peaks, the integration peaks gives us the ratio of hydrogens in each environment. Now, this is very technical, but it just means that the reason that you get a bigger hump of this one is because there's more of them to absorb, okay? So these 3 hydrogens are absorbing at this frequency. These 2 hydrogens are absorbing at this frequency, and this 1 hydrogen is absorbing at this frequency, okay? And because there's 3 times as more of these, all right, you get a hump that's 3 times as big. I hope that makes sense. Let me turn off Spotify for some reason. It keeps coming on and say, are we all good with that? I tell you, it's a very technical subject. It's a shame we're not at school, seriously, because it is complicated, this, without doubt. This is very complicated. But can I go on? Well, Natan says, yeah. Well done, Natan. Anyone else? What if we do? Yeah, we'll do propanol. We'll do propanol later. If you want, we'll do propanol in a bit. Okay, no problem. All right. Okay, so we will do it. Everyone's good for now. This is technical, eh? All right. Now, why do they? Your first question should be, well, why do these 3 absorb at different areas? Okay. Now let's have a look at this one here. Okay, the one on the left is a hydrogen. So I'm going to draw my hydrogen. There, this is this. Inside the hydrogen is a proton. Okay, and this hydrogen here is joined to this oxygen. Now we all know something about oxygen. Oxygen is very electronegative. Yeah. Now, and this is HC. So we're looking at this hydrogen here. Now, I'm going to take a rubber here, I'm afraid, and get rid of this rubbish for now. Okay. Because I need this space. Okay. So on this side, let's draw HA. Okay, this is my hydrogen. Okay, there's the proton. And this hydrogen is connected to a carbon. Okay, now, now let's draw the electrons. What color should I draw my electrons? Let's do them kind of this funny color. See those electrons there? Now these electrons are going to be pulled away from the proton. Okay, the hydrogen electrons are going to be pulled away, and they're going to be pulled away to the oxygen. Okay, so if you can think of it, now this is going to be really tight, but let's try and do this. The electrons around this hydrogen are not going to be as many as they are around this hydrogen. Oh, look at that, I've just messed up my nucleus. There you go. All right, so let's have a look at the electrons around here. There's going to be much more electrons around this one. Okay, and there's going to be less electrons around this one. So let's have a look at the proton here. So the proton here has few electrons around it, but the proton here has more electrons around it. Why is that? Well, because this proton here on the left is next to an electronegative element, all right, and the electrons are being stripped off of it. And this proton here, the one on the right, is next to something that's not very electronegative. So the electrons stay around it. Now, this one with its electrons taken off is called de-shielded, because the electrons form a shield. And this one with lots of electrons around is known as shielded. Okay, so this one is de-shielded, this one is shielded. Well, shielded from what, you may ask? It's de-shielded from the external magnetic field. Okay, and this one is shielded from the external magnetic field. Okay, now, don't forget, this molecule here is being subjected to a magnetic field. And this is a very important point. It's the same magnetic field across the whole molecule. Okay, now is an analogy time. I'm going to give you an analogy. Analogy. Okay, and this is important. Let's say it's raining heavily. Okay, here's the rain. Okay, and I ask you to go outside, all right, with your school, whatever, what you ever wear at school. So this is you. Okay, and this is me. Okay, but I'm kind of smart, and I go out with a raincoat or a poncho or whatever. Yeah, not poncho. Okay, not poncho, poncho, and a hat. Okay, now we would all agree that this is the storm, this is the rain. We are both in the same storm, but which one experiences, which one, this is you, and this is me. Which one of us will experience more of the storm? Well, it's going to be you, because you haven't got a raincoat on, and so effectively you are, I don't know where I can't write now, you are de-shielded from the storm, and I am shielded from the storm. Even though we're under the same storm, you experience more of the storm than I do. Now, it's exactly the same for this proton. This proton experiences more of the external magnetic field than the proton on the right. Okay, so now this is a big leap of faith here. So let me do my energy gap here. Okay, there's my energy gap for this proton. These are the aligned protons, and these are the opposed protons. What would this proton absorb at? It would absorb, if I give it this frequency E, delta E, is equal to HF. Okay, F1 I'm calling it. So let's go over to this one now, this proton. Now, the energy gap for this proton would be smaller because this is experiencing, the protons on these hydrogens or in these hydrogens are experiencing less of the external magnetic field. So the energy gap for these ones will be much, much less, will be less. Okay, so the energy gap is here. So delta E is equal to HF again, but this is going to be F2. But because these protons in these hydrogens, they experience less of the external magnetic field, that means their energy gap is less. Okay, and these ones experience more of the external magnetic field because they're de-shielded. Okay, I can hear someone's microphone again. Let's have a look. Okay, see if we can figure out who it is. We all need a break. Who is it? I'll find you. Oh, I can't see. Everyone looks good. No one I can see. All right. Anyway, so there you go. So what does that mean? Well, these protons, the de-shielded ones, will absorb different frequencies to these ones, these shielded ones, and that's why they absorb at different frequencies down here. Now these ones in the middle are somewhere in between. Okay, it's closer to an electronegative group, so it will shift it this way. So this part of our absorption curve is known as the de-shielded part. This is de-shielded, and down here, this part, these are called the shielded. Okay, so that's why you get different peaks for different protons. So if I didn't know it was ethanol, and I just saw this, I'd know, there's 3 different protons in ethanol, different proton types, and they are in the ratio 3 to 2 to 1. Okay, now that's a lot to take in. All right, I'm going to go to the questions now. I don't know how many questions we can answer really without me being there, but we'll see. All right, questions now. Also, we can't see your cursor. Yeah, I know. I've noticed that, Terry. That's annoying, isn't it? I always think, because I'm using the cursor hovering over things, thinking you can see it, but you can't. Oh, you can see it, but it's very small. Yeah, I know what you mean. I'll try and correct that. I know exactly what you mean. Okay, draw a tiny arrow there. I will, George. Thank you. All right, tiny arrow. Have you seen what I'm working with here? It's like Flintstone stuff. All right, so I'm waiting. So are we all good with that? With the basics so far? I promise you, going through the theory is a million times harder than the questions. The questions are so easy compared to what we're going through now. But I honestly don't know how you can do it without going through this hard stuff. Do the electrons around the proton interact with the field? They do. They do indeed. Yeah, they do. They shield the proton from the extent of the field. All right. The interactions are very complicated. I imagine you know that. Could you go over the de-shielding and shielding again? Yeah, sure. Okay, here we go. Now I've got to draw tiny arrows, apparently. Let me use a blue pen. Tiny, tiny arrows. Right, this proton here. Whoops. This proton here. This proton in there. That's a tiny arrow for you, George. This proton in here is next to an electronegative oxygen. Okay, so the electrons around this will be drawn to the oxygen here. And that's what I've tried to show here. So this proton is without its coat of electrons. And so we say it's de-shielded. This proton, there you go, there's tiny arrows again. This proton is next to carbon, which is very similar electronegativity to hydrogen. So this proton keeps its electron shield. So we call this shielded. Now, which one of these 2 protons, this one or this one, which one experiences the external magnetic field greater. It is this one because it's de-shielded. It's like having no coat on. You can feel the storm more. This one is shielded, so it can feel the storm less. Oh, excuse me. I don't think it's corona, don't worry. All right, so the energy gap for this one is going to be larger because it feels a bigger magnetic field. The energy gap for this one is going to be smaller because it feels a smaller magnetic field. Okay, does that help explain it, Madhav? All right. How does the pigs identify the type of bonding like infrared from last year? Well, we'll look at that. Don't worry about that, Hamza. Yeah, I know what you mean. If you look at the back of your data booklet, I'll show you, kind of. All right. Now, if you know the frequency they absorb at, let's say this frequency, you know, let's have a look at this one. This CH2. All right. You know this frequency. All right, you go to the data booklet, you look it up, and you'll see that if it's at this frequency, it's CH2. Okay, so don't worry too much about that. So that's that for now. Okay, let's go back to the questions. What are the protons shielded by? The protons are shielded by the electrons. If you are next to an electronegative element, you are de-shielded because your electrons are pulled away from you. Imagine you've got a younger sister, all right, and it's raining, yeah, and your younger sister wants your hat and keeps pulling your hat off of you, all right. She is de-shielding you from the rain, isn't she? Yeah, your sister would be electronegative. Now imagine you're next to a much more mature, older sibling. They're more likely to share the hat, aren't they? And they're shielding you from the rain, but an annoying younger sibling would take the hat away from you. They de-shield you, whereas the older sibling would shield you. Okay. Now, if you're next to an electronegative group, it's pulling electrons away from you, and it is de-shielding you from the storm that is the external magnetic field. I hope that makes sense. Yeah, electrons, I believe. Well done, George. There. I'll tell you guys, you've got to read the book. Eh? It's vital you read the book. Okay, so there you go. Now, this morning, oh, here we are. There's another one. Nothing. I don't know what that was. It's just some weird random stuff. All right, this morning, I was talking to the Form 4s, I think it was, and I went over 40 minutes. And I think this program only allows conversations for 40 minutes, or the Screencastify did only 40 minutes. So what I'm going to do is I'm going to stop here, all right, and try and understand all of this, read the book, and we'll start next lesson going into this again. Now, look, let me tell you this. It's not an easy subject, this. I don't think you can even approach a question yet, but you'll be amazed. Once you do start doing the questions, they're so easy. All right, but this is nice stuff. It's hard stuff, but it's nice stuff. I might be confusing myself here, but the electrons have spin too, right? Is it because of the frequency that electrons will be absorbing compared to the hydrogen? I don't follow you, Terry. I must admit. But the electrons have spin. Yeah, the electrons do have spin. Is it because of the frequency that the electrons will be absorbing compared to the hydrogen? Yeah, I'm sure the electron density around a de-shielded atom will be less, won't it? So the proton is what we're flipping. Now, the electrons will interact with the external magnetic field, but I don't think it will actually make much difference compared to how the proton will interact with the external magnetic field. All right. I kind of know what you mean. Everything, protons and electrons will be affected by an external magnetic field, but don't read too much into it, eh? All right, we are in a chemistry lesson, not physics. The physics would be interesting, and and it is a very complicated topic. This about what's going on. Seriously, it is. All right. So anyway, so it's 37 minutes, I'm afraid. The integration peaks where the resonance goes. Yes, exactly. Well done, Nicholas. Where you get resonance, that's right. When you hit the right frequency, the electrons start to flip. They go from the opposed state to the, they go from the aligned state to the opposed state. And when you hit exactly the right frequency, they all do it. All right, they all start resonating. In other words, they all jump up. And at resonance frequency, we see an absorption peak. But don't forget, not all of the protons will resonate at the same time because they are experiencing different external magnetic fields. Okay, I hope that makes sense. All right. Right, guys, well done. So tomorrow you have a day off from me. And then what day's tomorrow? Tomorrow's Thursday. And then Friday, 10 o'clock. Okay. Anyway, guys, well, thanks for coming. We are slowly getting there, trust me. All right, it's taken a while, but well done. All right, have a nice night. Good night.